Welcome back, everybody. Okay, so we got the rationals now. Final step is the real numbers. So the real numbers, how do we build the real numbers from the rationals? You guys know? So what is the idea for the real numbers? So the real numbers, we have the rationals, right? Let me draw. It's hard to draw the rationals because you have 0, 1, 2, -1. And then you have the fractions in between, the halves, the third, the fourths. Okay, so I don't know if that looks like the rationals to you guys. Anyways, the rationals are like in a line, but they are full of holes. Like if you want square root of 2, e or pi, they are kind of square root of 2 is somewhere there in between. But it's not a rational, it's a hole there. So to get the reals, we need to fill in all the holes, right? So that's essentially what the reals are. It's like it's a completion of the rationals, filling in all the holes and getting the full nice line right there containing all the points. Yeah, so that's what we want to define the reals. So there are a few ways to do this. One of the most common ones is Dedekind cuts. Cauchy sequences is another one that maybe you saw in another course. They're equivalent, Cauchy sequences and Dedekind cuts. We're going to use Dedekind cuts in this class. Again, we're going to use them for these videos. After that, after this week, we're going to be set with what the rationals, reals, and the integers are, and we just work with them as reals. We don't the particular definition that we are giving today. Now, so what is a Dedekind cut? A Dedekind cut is a subset of the rationals, the subset of the rationals, which is neither empty nor everything. Okay, so it's what is called a proper subset. It's not trivial, it's not empty, and it's not everything. So okay, the second property is that x is closed downwards. What does it mean? That if wherever you have p and q in the rationals, and if p is less than q and q belongs to x, then p also belongs to x. Okay, so that means if it has something in x, it has everybody that is below it. All right, so that means if you have x, let's say x is something like a set, that is gonna be like that, and if there is a q that belongs to x, then everybody that is below x, below q also belongs to x. So that means if it has one point, it has all the previous one. If it has this one, it has all the previous one. So it's what is called an initial segment. X is going to contain from, whenever it has one, all the previous one. And it's going to have no largest element. Okay? So there is no element up there. There is no supremum in the rationals for X. Okay? So that's the three properties that define a Dedekind cut. And the idea is that the Dedekind cut is defining that point. So you think of a Dedekind cut as cutting the reals between the ones that are below the element that we are defining. Those are the ones that are in X, and the ones that are above that are the ones that are not in X. Okay, so it's cutting the reals, the rationals in two, and so that's what the reals are. So the reals is going to be the set of all the Dedekind cuts. So all the places where you can divide the rationals in two pieces, left and right. Cool. So for instance, the number square root of 2, the real number square root of 2 is going to be equal to that, the set of all rationals such that r is less than square root of 2, right? Okay, so that's intuition because we don't have square root of 2 yet. So suppose we are trying to define what the real number square root of 2 is. We cannot use square root of 2 in the definition. So we will have to say, what? We will have to say that r squared is less than 2, right? If we get everybody that r squared is less than 2, we are gonna get all these guys. All these guys here, all these guys here have r squared less than 2. Is that correct? Well, actually, if you do that, we are gonna end up also all these guys here have r squared less than 2. But only up to negative square root of 2. So that's not exactly what we want. We're going to say this union all the r's that belong to q such that r is less in the rationals than 0. And by the way, that 0 and that q are and the 2 are the rational numbers, 0 and 2. Okay, so now if we do that, then now we get all the points, all the rationals that are below what's supposed to be square root of 2. We don't have square root of 2 yet, but if you take all of those that satisfy this property, and by the way, also, let's just clarify, when we say r squared here, we mean, what do we mean? We mean r times, using the rational multiplication, r. Good, we have that multiplication. So we get this set, all the things below square root of 2. And that's what we're going to use to represent square root of 2. So actually, when we say square root of 2 back, if you look at the nuts and bolts of what's going on, we're thinking of that set. Okay, so those are the Dedekind cuts, and that's the idea. So what is going to be our embedding? Now we want our embedding from the rationals to the reals, so that we can see the rationals being inside the reals, the way we wanted before. And so what it's going to be, it's going to be the obvious thing, it's going to be all the r's that belong to the rationals, because the Dedekind cuts are self-rationals, such that r is below, according to the rational, to q. So one point to make here is what would have happened, what happens if we consider, why not considering r in q such that r less than or equal q? That will be the same cut essentially, right? The q will still be the point that is in between the things to the left and the things to the right. But this one doesn't satisfy the property that has no element, because this one has a largest element. So we don't consider this guy as a valid Dedekind cut. And why is that we don't consider it a valid Dedekind cut? It's because if we do, then we will have two sets, this one and this one, the two of them representing the same rational q. Right? The supremum of this set is q, the supremum of this set is q, and we want just one representation of q, so we have to choose one. And this one makes sense because when you have an irrational, you're not going to have a supremum, so this one works for rationals and irrationals. By the way, an irrational number is one that is not rational, right? So that's why we put the no largest element assumption, so that we have only one representation for these guys. Okay, so now that's how we fill in the gaps. So every element, every real number, if you want, let's say now number e, in this picture, number e is going to be somewhere here. It's going to correspond to all the rationals that are below some point over there. It's a bit harder to define, but you can define it with the formula. You can use the subset axiom to define all the rationals that are below E using the series representation of E, maybe, and write down a formula in first order arithmetic that defines all the rationals that are below E, and then you have the number E. Cool, okay, so we have the reals and we can see the rationals as being inside the reals. How do we find order on these guys? It's just inclusion, right? Because, I mean, x is an initial segment of the rationals, and y is another one. So being less than or equal, it just means that one is inside the other. So there is nothing to it, it's just inclusion of sets. And what is the property that's of the order? Before going to operations of arithmetic operations like plus and times, the order in the reals has two main properties. First is that the rationals are dense inside the reals. So what do we mean by that? We mean that for every x and y in the reals, if x is strictly less in the reals than y, then there is a q in the rationals such that x is less than q is less than y, right? So whenever you have two reals, you have a rational in between. That's what it means that they are dense. There is no segment that you can find which has no rationals inside. And just let's be very picky, just for today again, about what do we mean here by less than. So these are reals, so this should be the less than on the reals. This should be the less than on the reals. Q is a rational. So it's not a set, so we couldn't use this same definition if Q is not that real. So actually what we mean here is E of Q, the embedding of Q inside the reals. And again, this level of pickiness is only for today that we are defining the reals and verifying that it satisfies the right properties. After we have the reals and we know that the rationals kind of embed inside, we can assume they are a subset, and that's it. Cool, how do we prove this? Let's do a little proof for today. So how do we prove this? So we are given x and y, and we know x, so we know that x is less than y, and what does that mean in terms of definition of less than or equal on the reals? So we know that x is a subset of y, and not only we know it's not equal, it's strictly less. So that means it's strictly included in y, because otherwise y would be also less than or equal x. Right, so if there's strictly included, then there exists a Q that belongs to y and not to x. That's what it means that is strictly included. This is at least one element in y that is not in x. Cool, and it has to be a rational because y is a set of rationals itself. So everything that belongs to y is a rational. And then what do we have? So so we have two claims. So no R in x is above q, because otherwise we will have q will belong to x, right? Because x is closed downward. So if you have somebody in x that is in somebody above q in x, then q will have to be in x. So that means that the set of r's that belong, so that means x. Let's just write that. This just means x is a subset of the set of r's in the rationals such that r is below q. Right? And now q belongs to y, and y is closed downwards, so that this guy is a subset of y. Because q belongs to y, so everybody below it also belongs to y. So that's how we get what we want. X is less than in the reals, q less than in the reals, y. Cool, so the rationals are dense, so that means rationals are everywhere. So one of the main theorems about the reals is this one. It's called the completeness of the reals. Nothing to do with the completeness of the language or completeness of anything of logic. It's just about the real numbers. And it's that every subset of the reals that is bounded above, that has a least upper bound, every subset of the real that has an upper bound has a least upper bound. Okay? So maybe let's just do a little picture about what that looks like. So if you have, if you have a set A that contains a bunch of things, and you know it has an upper bound, meaning that everybody is below that red line, then what the theorem is saying is that there is a least among all the upper bounds on the reals. That is here. This is the least upper bound. And this one here is just an upper bound, but it's not the least upper bound. Yeah, so what is an upper bound? So an upper bound, it's a B is an upper bound for A if for every x that belongs to A, x is less than or equal. Okay, so that's an upper bound is something that is bigger than, it's a bound, it's something that is bigger than everybody in the set. And a least one is the one that is least among all the upper bounds. So what is your guess? What should be the least upper bound of a set A? I'm gonna move this up here. What do you guys think? Well, we have this, remember this is a union operation. So what happens if we take the union, so let X be the union of A. A is a set of reals, so each real is a Dedekind cut. So each real corresponds to each real here is everybody below, right? Every real in A looks like this. There are some reals that are in A, some not, but all of them look like that. If we take the union, we're going to end up with what? We're going to end up with a Dedekind cut. And we claim that is an upper bound. So why is that? So I guess we have to do a few claims. So first, X is a Dedekind cut. And for that, we need to show a few things. It's not empty. So X is not empty because A is not empty, and all the members of A are not empty. X is not everything because, why is it not everything? Well, because we have a bound. We have this bound B, and the bound B is not in A. Well, it's above everybody in A, because if you have a Q that is an integer and is larger than B, then for every Y in A, Q is not in Y, right? So whenever you take a Y right here in A, and you took this Q that is right here, something bigger, Q is not in Y, right? So if you take the union of all these Y's, then it's not going to contain Q. So let's just remember that this here means the union of all the Y's such that Y belongs to A. That's essentially A. So you're putting all these Y's together. So if you take some rational bigger than B, it's not going to be in the Y, in the union, so the union is not everything. So it's downward close. Why is it downward close? Because every Y that is here is downward close. Right? So if somebody belongs to the union, it belongs to some element of A, and then everybody below it will also belong to that same element of A. So that will belong to the union. And it has no largest element. Why does it have no largest element? Well, because if it did, the largest element will have to belong to one member of A, right? Because it's in the union, so it has to belong to some member. But then it will be the largest element of that one, right? And that cannot be the case, because nobody in A has a largest element. So the union of A is a Dedekind cut. X is a bound for A. So I'm saying X is greater than or equal Y for all Y in A. And that's just nothing. That's because Y is a subset of the union of A, which is X. So Y is a subset of X. Why is it the least upper bound? So suppose Z is below, strictly below X. Then we claim that Z cannot be an upper bound. And then, so why is that? Well, if this is the case, so here is our X. Right here is our X. And let's suppose that one is our Z. Well, it's strictly below, so it's strictly included, the same as before. So then there exists an R in the rationals that belongs to X and not to Z. So right here, that's our R. If it belongs to X, X is the union of everybody in A. Right? X is the union of everybody in A. So something belongs to X, it belongs to somebody in A. There exists a Y in A such that X, such that R belongs to Y. But R is not in Z, right? So here we have that R is not in Z. So we cannot have that Y is included in Z because R is in Y and not in Z. So that means Z is not an upper bound. So we took something that was smaller than X and we show it's not an upper bound. So then X is an upper bound, so X is the smallest possible. Nothing below is an upper bound, and itself is an upper bound. So it's the least upper bound. Okay? So that's how we get that every set, if it's bounded above, it has the least upper bound. And that's the way of saying that every hole between the rationals is filled in. That's the way mathematicians have to say that. That is, it satisfies this property. That whenever you have a set, there is a maximum, a supremum, which is not true of the rationals, but it's true in the reals. And then we need to define, as usual, the properties of addition and multiplication. It's a little bit of a trick. So if you look at addition, it's quite simple. We just take all the rationals that are below t plus s, where t is in x and s is in y. Okay, so each one is a set of here you have x, here you have y, you want to add them, so you say, well, take all the ones here and all the ones here, add them, and then you're gonna end up with something x plus y by adding all these guys. Adding this one and this one, you add them, this one and this one, you add them, you add all of them, and you're gonna end up with x plus y. So add all the rationals below x, all the rationals below y together. And that's your x plus y. To show that this is closed downwards, it takes like a line. Not too hard. What about multiplication? Multiplication, we could do the same trick. Let's try it out. Let's see what happens if we say that the multiplication is the set of all the r's in Q such that there exists a t that belongs, I'm going to leave some room here, x, and there exists an s that belongs to y such that r is below t times the rationals s. Cool. Similar idea like this one, I guess. You have the numbers below x, you have the numbers below y, you multiply them together, the rationals are getting very close, the ones in x are getting very close to x, the ones in y are getting very close to y, you multiply them together, you're getting very close to x times y. Sounds wonderful. There is just a little annoyance, and is that x contains everything below it. In particular, it contains the numbers that are negative, all the numbers that are negative. Or if x is negative from that point on, and y is the same. So if you take minus a million that maybe belongs to x and minus a million that maybe belongs to y, now you have positive 1 trillion that you're claiming it should belong to x times y. And that's not what you want, right? Two big negative numbers are gonna give you a huge positive number, and actually you're gonna get all the numbers that doing this. So that's not good. So let's only multiply the positive numbers right here. So I'm gonna put in the interval 0x and in the interval 0y. I'm gonna let you guys try to guess the definition of what does it mean to belong to the interval 0x and 0y. That's quite straightforward. And now we don't have the problem with the negative numbers. Well, first, this only works if x and y are positive, right? So this is, if they are positive, then this works. Well, not exactly, because again, we're only getting positive numbers and we want to get everybody. So I guess we will have to add all the negative reals, all the negative rationals. And now, yes, now we got what we want in the, I guess, in the positive case. Now we had x is here, y is here, here is 0. Now we're taking all the elements here, we multiply them together, and here is x, here is y, here is x plus times y. We multiply them together, we get this. We're gonna get only by multiplying them together with everybody here below x times y. And now by force, we added all the rationals that are negative, and we end up with a Dedekind cut for x times y. Good. What would you do if x and y were not positive? So you need to divide by cases for sure. You need to divide cases when x negative and y positive, both negatives, x positive, y negative. So they have 4 cases. And in each one, you can either directly define this thing, or you can use what you expect should be true, which is in the definition you say, well, if x is negative and y is positive, you just take the inverse of x, multiply those guys, and then take the inverse again. The inverse, not the negation, the minus. Yeah? You need to define what it means to be the negative of a number, but it's not hard. So there are a few cases you need to consider. Look them up. They are what you should expect. And again, it's always good to try to think about what you're gonna get before you look them up. Cool. And then the last thing is you need to show that this map that we define right here is an embedding of fields. Actually, these two are fields. So, well, in particular, it's an ordered ring homomorphism. That's the same thing, but they are both fields. So it's a field homomorphism. It's one field inside the other one with all the same operations satisfied. By now, we have all the gaps have been filled out. And, well, that's after we show that these guys are filled, that the reals are filled. What does it mean to show they are filled? Associativity, commutativity, distributivity, inverse, order preserves plus, order preserves times, 8, 9 properties. You need to prove them one at a time using what you know about the rationals to now prove this about Dedekind cuts of reals. It gets a bit messy because multiplication now has these 4 cases depending on the signs of the x and the y, and then when you look at these properties, you have to look at all the different cases. None of them is hard. Every proof is a line, but then there are more cases and cases, so you need to do that. Okay, so now once all those little proofs are filled in, now we have something that looks like the reals and behaves like the reals and flies like the reals, and we got the reals, and that's it. So now we have math, like great percentage of math is on the reals. So wait, we have on the reals, we have functions. We know how to do functions, so that means we can do functions from reals to reals. We know how to do Cartesian products, so we can do R square and R cube. So now we can do like linear algebra on R cube, R square. We can define functions, so we can define continuous functions. We can look at what it means. We can define limits. We can define what it means differentiable function. The complex numbers are just pairs of reals. So now by now you should be able how to define them. So we get a lot of calculus, a lot of analysis. Algebra is not too hard to define. Everything is defined in terms of sets and operations. So yes, so all of math, everything that you learn in all your math courses so far, and that you will learn in your undergrad and probably grad school, you can do here with these axioms so far. And we haven't even finished with all the axioms, but the axioms that we have so far are good enough for like 99% of mathematics. You like rarely go beyond these guys. So cool. We started only with a symbol for begins, for belongs. We began with a symbol for belongs, and a few axioms that you all agree in class that they were all basically obviously true and they presented no issue at all. And now we have a system where we can develop all of mathematics. So that's pretty strong. So that'll be it for this week. So next week we are going to start building cardinals. See you next week.